I'm Peter Taborek. I'm in the physics department at UC Irvine, and I want to tell you about a course that we have developed here for to teach basically mathematical methods to physical science students. It's based on a an electronic, a Mathematica-based book called the Mathematica Handbook, and we've also developed a web-based grading platform to automatically grade uh, undergraduate level math methods problems. I want to describe what the content and kind of what these courses are all about, and then the motivations for developing this new version. And I'll give you some examples of the undergraduate version of the class and the graduate version of the class. So, all right, let me explain sort of what this course is all about. Students in engineering physics, physical chemistry are required to take courses that are typically called something like mathematical methods in physical sciences or whatever. And they're offered both at the undergraduate and the graduate level. And the reason for these courses is that the preparation that undergraduates get in their math classes, the type of skills they develop there, are really not the type of skills that we need in sort of the physical sciences. And we really, they can't succeed at problem solving in physics and engineering without additional help in practice in those kind of skills. And they're just a little bit different than what they get in their math courses. And so it's a standard thing at both the undergraduate and the graduate level. There are standard books to do this, and here's a list of a few of them. And they are, and they all have titles such as mathematical methods, in physical sciences, in engineering, for science and engineers, and so on. And these are, again, very standard courses, and there's at least 35,000 students per year take these classes in the US, and of course, many more internationally. Just to give you a flavor for what's in them, this is sort of the table of contents of two particularly well-known books. One is the Boas, which is sort of a standard in sort of undergraduate physics, and Krasig, which is a standard in undergraduate engineering. And the content overlaps between the two. So there's always stuff about complex numbers and complex variable techniques, and the weighting and the order is a little bit different depending on the class and the book. But there's complex analysis, and here it is in the engineering thing. There's lots of discussion of linear algebra. So there's linear algebra, matrices, vectors, etc. Basically a review of vector calculus applied to things. So there's a vector calculus thing. Lots of stuff on Fourier series and transforms, and you'll see that the chapter titles, there's lots of overlap. So lots of discussion of ordinary differential equations, and the weighting is a little bit different here. There's special functions and series solutions, PDEs, probability and statistics. So all these sort of standard topics are common to all of these books, and with slightly different weighting, and they're very similar. These books all cost over $100. The first edition, they're sort of classic books, and the first edition of these books was written in the 60s, and they've gone through many subsequent editions. And in the 60s, this was before the era of personal computers, but there have been many subsequent editions, and the newest editions sort of acknowledge the existence of computers by adding things to the problems, such as use your computer algebra system to check your results. That's the level at which they acknowledge computation. There have been some more recent books that are explicitly for Mathematica. Here's a couple of them, but these are still sort of dead tree books. They're books with in the standard format, but add a little bit of Mathematica. So I started developing a course. I started actually about 15 years ago, and I took up the challenge of trying to make a kind of a modern version of this that was completely electronic. So it consists of Mathematica notebooks, and some of the motivations for making this thing was to reduce the textbook cost, because the textbooks are expensive. The the typical problems in the standard books are solve this differential equation, find these eigenvalues, and they're sort of computationally not in computer sense, but just doing calculating some number or some equation. And I wanted to reduce the emphasis. Those skills are just not what we want our students to learn and to perfect, and rather emphasize understanding of algorithms which solve a wide class of problems. And in general, to develop modern technical problem-solving skills. The sort of 60s, the skills that were required in the 60s are, they just changed, and the way that modern technical people solve problems is really quite different. And I wanted to make a book that acknowledged and addressed those problems. So the criteria for this textbook are, one of the first ones is that the topics, you can't get carried away with innovation. The academics are surprisingly conservative, and there's a hierarchy of skills, and there are prerequisites, and you can't change things too fast. So the topics of whatever you generate here have to overlap whatever the conventional course is. Another problem is that if you're going to use Mathematica a lot and you have naive undergraduates in your class, you really have to provide a pretty serious introduction to Mathematica so that they can do whatever is going to happen. You want to utilize graphics, manipulate, animate, and use that in a maximal way to illustrate concepts. Mathematica is full of relatively high-level, beautiful commands that do interesting things, like residue, matrix, exponential, asymptotic, d-sol value, etc. But to use these in an intelligent way, you really have to understand what the algorithms are doing. So the way that I try to do that to the students is basically to go through one calculation by hand to see what is going on, what the algorithm is. And then once they master the algorithm, they're free to use the higher end Mathematica functions. And then you can use Mathematica. The other thing that you want to use in a modern textbook is to use Mathematica to leverage the power that you get to solve more complicated and more relevant, more interesting problems that arise in subjects that they're going to address later: classical mechanics, quantum mechanics, fluid mechanics, or whatever. This book is now available at a website. You go to this website and you can download it. And what it does is generate, there's about 100 notebooks in it. It's about 150 megabytes of material. And it generates a palette that is the thing that lets you go to it. And I'll show you the live thing in here in a minute. But one of the things I mentioned there was that you have to teach a little bit of Mathematica, otherwise you can't proceed with these students. And some of the things that I found that require attention, and they're kind of obvious, but that just things, they're sort of syntax issues that have to get addressed before you can proceed. And so you have to explain the difference between equal, double equal, colon equal, etc. The whole / dot operator is needs explanation in practice, otherwise they don't understand it. Things that cause a lot of frustration and confusion are the fact that the square root of x squared is not x, and the real part of x plus iy is not x unless you provide assumptions and assuming. And similarly, just get used to the idea that you do sine square bracket x, not round parentheses, and that things that come from printed mathematics that you think would be obvious are just require assumptions, and you have to do all that. Let me show you how this thing works now in a live way. So once you've downloaded the book, it generates a palette, and the palette, the tool looks like this. So well, all right, there's a tutorial section, and let's talk about that first. So the very first thing they do, this brings up a notebook. And the format of all these notebooks is a bunch of statements and sort of an outline of what's going to happen. Typically, there's sort of an introductory paragraph that says what's going on, and some hyperlinks to issues that you're trying to make. So how to use basic elementary functions, how complex numbers work, etc. There are built-in quizzes into this, so you can push on this and they'll give you a quiz and you can get the answers here. And it goes through, how to use an elementary function, how to set up equations with double equals, how to do basic calculus, how to do lists and matrices, how to understand how to use slash dot, etc. So and this kind of material takes roughly, basically in two lectures, I managed to get them to do basically everything they need to know. There's another thing that's important for people in physical, that are going to study the, science and engineering are kind of using vectors and integrals and these issues of, how to use power expand and assuming and assumptions. And so there's another notebook that explains all that. And it does that by sort of typical physics problems, damped harmonic oscillator, calculating the magnetic field from a current loop, and statics, a simple statics problem, how to set up linear equations that help you understand forces and so on. This is all put together. There's a cheat sheet, which is pretty popular, which is, for an undergraduate class, you really need to understand about 20 functions, and here they are. And if you want to, and it just illustrates how to do some of these things. So, and really you don't need to do too much. It takes a lecture or two, and the students are really pretty good at doing it. Another thing I mentioned that is good to do is to use to use the power of Mathematica to illustrate more complicated stuff. So let me show you a few examples of that. So, well, all right, let me first point out again that after you've done the tutorial, there's tutorials, and there's more advanced things in here. There's just a review of all the possible, sort of a quick review of plotting capabilities of Mathematica that so that students can quickly refer to things like that. But other than that, the titles and the subject matter mirrors the conventional books pretty well. And so there are, all the standard topics are covered in here in that standard way. So, but there's some additional things. Well, wait, hold it. Let me do this complex things first. So this opens a notebook, and this is sort of a typical undergraduate level thing. By the way, there are, for all the introductory subjects, there are videos associated with it. So I myself tend to like to read things, but I know that some students just like to hear stuff, and there's videos that will guide you through these notebooks. And just to leverage the imaging capability of Mathematica, there's nice diagrams in here that discuss various things. And when you're talking about complex functions, there's a number of ways to illustrate in a nice, clear way how complex functions work. It's a hard thing for undergraduates to understand the difference between f of x, a real variable, and f of z, a complex variable. And here's a way that here's a tool that helps them do this. So this is a thing that it writes w is some function of z in the z plane and maps things into the w plane. And this is, and you can type in any function you want in here. So to show students that e to the z is not the function that they think it is, or it's not simply the real value function. You can just draw a picture in the z plane, and it immediately maps it over into the w plane. So you can see the image of anything you want. And so you can understand, how it just gives you a visceral feel for how these complex functions work. So that's one example. I mentioned that using this thing for other problems. So there's a whole thing in here that it wouldn't be in a traditional book, but it's applications and case studies. So it covers a bunch of slightly more complicated problems that are computationally intensive. A standard problem in any E&M class, electricity and magnetism class, is reflection of waves off of an interface. And the algebra, it's in all the books. The algebra is rather complicated, and it's a perfect thing to illustrate computer algebra to actually solve it. And it boils down to satisfying some boundary conditions and setting up a system of equations that you can just solve. But the solutions are complicated. They're complex and rather complicated. So what do you do with them? And we can use various techniques to draw some of the traditional plots. But we can also do this kind of thing where, it does a simple manipulate, but it illustrates this is a vector wave, so there's polarization involved, and we can look at the how much energy gets reflected and transmitted. And you can say, for instance, that there's a magic angle, which is a Brewster angle, where all the wave goes in, but then as you increase it, it goes away, and so on. And there's many of these in this system. Let's see. In order to make a course out of this, you really need to provide practice and feedback to the students. And the problem is that it's time-consuming and expensive to grade. So I want to show you a system that we've developed. This was developed by a grant from the state of California to develop affordable web-based education. And we have used it to do some of these math methods things too. So this is the platform. This is the way it looks. And it's organized around libraries of questions. And we have many of them. There's physics, chemistry, various levels of physics that are used at community colleges, and conceptual sort of physics for poets kind of things. We have some chemistry. We have a complete set, and there are thousands of questions in here, all of which have nice solutions. So the way you can look at this problem, and there are solutions that are provided to it, and those solutions would be available to the students. So there's many things. The things I want to talk about are mainly this math methods. And let's see what I'll show you first. Where am I? Yeah, okay. Let me show you how an instructor would generate a set of problems. Let's just call this demo 1. We'll create it. And what we typically would do, you can write your own questions, but you typically get a library. And then this is a library for undergraduate math methods. So let's say we want vector calculus problems. Let's take a look at this one. So it's evaluate some line integral. We look at it. It's got a couple parts. We can quickly look at the solution, see if it's what our students, whether our students are ready for it. And the format for all of these things, by the way, reflects a concern of other faculty that the students learn how to do this all by hand in detail. So the format of all the answers are do it in detail, essentially by hand, where you could have done it by hand. There's an answer, and at the undergraduate level, the answers tend to be simple, like -2 pi. And then it always has a check with how you would do this in Mathematica. So it also teaches them how to do things in Mathematica. But you can sort of see whether that is what you want your students to be doing. If you like it, if you think that's the way to go, you just click that button, and you can look at some other ones. You can look at this one and say, do I like that? I can look at the solution, see if it's good, and say, yep, that's what I want. And now I've got a question set that I can add to a course. So And it will, and well, let me look at it. All right, so this is actually a live course that one of my colleagues is using to do this. And let's see, well, wait a second, let me show you what it looks like to a student. Now, to a student, it looks like, look at an old homework problem. So these are, so it looks like this, and the students can either do it on paper and pencil and type a number in here, or they can copy and paste from Mathematica if they want. And it gets automatically graded. So they get immediate feedback into whether they got it right or wrong. And from the instructor's point of view, so this is literally a course that's going on right now, and it has roughly 100 students in it, and the system is automatically grading all these things. And if we look at, this is what a student, this is a homework that was due, I think, last week. And so here are some of the inputs that the students put in, and they got it correct, and so on. And there's another feature for all these problems. The problems I've showed you so far have sort of simple symbolic solutions, but you can also have them upload a file. And for something that to show a proof or whatever, you can have them actually upload a file, but you have to grade that by hand. So that's how that system works. And it's been quite effective, and we've done it for mathematics, and for physics. Let me give you a quick sort of idea of how the grading algorithm works. So we have sort of the general purpose symbolic grader. The website these are API functions, and so the website sends a message to a function that is on the Wolfram cloud, and the first thing you do is make sure that it syntactically makes sense. And then we do some string manipulate. There's a lot of E&M problems that have epsilons and mu's and all that. We take care of that. And basically the idea for the simple stuff, an algorithm that seems to work pretty well is figure out what if there's symbols in both the student's input and the correct answer, we find those symbols and then basically assign random numbers to those symbols. So we turn it into a numeric thing, and then you also have to check sort of the basic structure of the answer. If it's a list, is it the right length? Is it the right structure? Is the answer? And then you send back yes or no to the yes or no, or you can give hints and about what kind of errors got detected, and that generates the score, and you put those in the Wolfram cloud, and it's been working very well. For non-unique answers, there are a bunch of problems where you can't just simply say, is this equivalent to the correct value? And we have special functions that do that. And a typical example is a solutions to equation or finding the eigenvalues. There's no order to them, so you can't just say, is this the same? And so you have to write some special code for it, and that's easy to do too. We have a graduate version of this, and the subject matter is similar, but it's sort of at a higher level. So at linear algebra, we discuss some of these things, but we include things like pseudo inverse, singular value decompositions. We talk about fancier complex analysis, and so on. Let me show you a typical homework assignment. So this is the graduate version, and this, of course, you cannot grade these automatically. So the format in this thing is the homework is assigned as a notebook and then turned in as a notebook, and I'll show you what that looks like. So this is a homework assignment involving different trying to explore the differences in asymptotic solutions in a linear and a nonlinear system. This is another nonlinear equation problem. These are some asymptotic evaluations of integrals, a perturbation problem, a simple PDE problem. And then one of the things I emphasize to my students is that this is typically a first-year graduate course, and I emphasize to them that this is basically the last time that they will be in an exam room where their performance is judged by a timed exam in 1 hour, and that's a more realistic thing is that they're going to be working on problems that take them months and years, and they're going to do this with many people. They're going to have collaborators and so on, and therefore technical communication is very important. That you have to be able. It's important to both so you can go back to your own work 3 months from now, and you can communicate with your boss and with your collaborators in an effective way. And Mathematica is great at that, and I encourage I basically teach my students how to do that nicely. And so let me show you what so that notebook, I give them that notebook, and this is sort of the flavor of what comes back from them. And they learn to do beautiful plots. They do nice explanations of what they're doing and why they're doing it. They know how to use the graphics very well. They get carried away actually with funny simulations of stuff and so on. So you can see that they do a very nice job, and it's readable, and it carries over into their subsequent research work. And I want to contrast that. Actually, I think I have a picture of that somewhere. Yeah, this is what my more conventional colleagues get as a response to a homework problem, and you can I think you can appreciate the difference, and it just prepares the students for the real world in a much better way. All right, let me summarize what I've said. I've developed a completely notebook-based textbook for mathematical methods course, and it can be used at the undergraduate level or the graduate level. And it's sort of a plug-in compatible with the standard courses, and it can replace the standard books. It covers the same material at roughly the same level, and there's a gradation of levels, so you can use it either undergraduate or grad. And then we have built a web-based platform that has thousands of questions with nicely formatted solutions, and leverages Mathematica to automatically grade that stuff. And we've used it, the same technology is used and actually gets used more for grading, basically undergrad introductory physics classes and chemistry. And if you or your colleagues have any interest in using these technologies, I would be very happy if you got in touch with me and we could, explore how to do it.